Okay, so what I'm going to talk to you today about is inline angular optical multi-point scatterometry for nanomanufacturing systems. This is the people involved are my postdoc Juan Faria, who was my student and has done a lot of this work, and myself. This is all funded as part of a NSF Engineering Research Center that's headquartered at UT Austin. So the idea is that angular scatterometry, which is essentially reflectivity as a function of angle of incidence from a periodic structure, uniquely provides non-contact, all optical, non-destructive fabrication monitoring. We're extending it to high speed, and you'll hear a lot about that in the rest of the talk. It works at the nanoscale down to 20 nanometers, part of what we're doing as part of this process is going across the web as well as one point on the web. So the sequence is we started out with a static system, and the static system is shown here. It's just a laser. You monitor the reflectivity. You have have two stages that rotate so that the detector is always looking at the reflected light. And the good news is you get excellent results, which I'll show you. The bad news is you have to clip off a piece of the web to do it, and it takes you about a minute to do a scan. We've now demonstrated an online system, which is outlined over here, and where we scan the beam with this resonant scanner. And so this, if you see this lens, you see the yellow on the top and the red on the bottom. That's the angular scan. Right. We scan up and down that thing, and that ends up scanning across the web and giving us the angular scan. So, well, this took a minute. This takes whatever I said it took, which I can't read, 45 microseconds. Okay, so some background is there's increasing activity in roll-to-roll and flexible electronics manufacturing. I'll give you some numbers in a minute. Fabrication techniques, as always in electronics, are moving towards smaller features following the integrated circuits industry. Roll-to-roll manufacturing is harder than the integrated circuits industry because you're not working on a stable silicon platform. You're working on a web that can move on you, and that if you're not moving the web smoothly, it'll do all sorts of funky things. So that means that real-time metrology is a critical need, and that's been the driving force behind this whole project. And some applications are listed here. Some are big already, which is wire grid polarizers for displays and advanced solar cells with surface structure increased absorption. Some are coming, the metal mesh grids for transparent contacts. Right now, ITO is the dominant technology, but there's only a limited amount of indium in the world, and it also doesn't work very well on flexible things. And metamaterials is a growing new area that requires nanoscale features. Okay, so here's some idea of the market. In 2019, the global market for flexible printed and organic electronics was $37 billion. It's growing at 11% a year. For IC manufacturing, metrology now accounts for about 20% of the manufacturing cost. But in roll-to-roll, it's going to be worse because the tool set is not nearly as well developed. As I mentioned before, there are many more degrees of freedom for the web motion, which means you have to monitor it while it's happening. And the silicon industry uses statistical process control. So they go offline, they measure it, and they measure a small subset of what they produce, and they're happy. But roll-to-roll can't do that yet. So here are some results with our offline system, just to give you an idea of what we can look at. And actually, let me look here. So this pattern, this is a wire grid polarizer. These are aluminum lines on 100 nanometer pitch. They're about 50 nanometers wide. And they're, I don't remember how thick they are. They're about 200 microns, 200 nanometers high. And we ended up, in terms of fitting the reflectometry, we ended up with 8 parameters. And you can see over here the fits we get. The scatterometry is an indirect measurement. You measure a signature and then you compare it to various models and figure out what the pattern looks like. And we were the first to do this at multiple wavelengths, and we needed all of these parameters to get the wavelength, to get the numbers we measure at each wavelength to match. And here I'm showing you a simulation down to 20 nanometers so that there's lots of room to go. And a number of publications are listed here, so you can see we've been active in this area for a while. Okay, here's our real-time system, and I don't know what happened to the, there it is. Okay, so here's the real-time system. Now we have this resonance scanner that's scanning the beam from the yellow to the red and back, and this is at 8 kilohertz. So if you look at a reflectivity trace, instead of taking a minute to do it, we're doing it in 45 microseconds. And here's the actual device that's doing it. The web is down underneath here. And there's some parabolic mirrors that are doing the focusing. That's these guys. And I won't go through this in detail, but here's the proof that it works. So what we're showing you here is two different structures. One is a 1D structure, one is a 2D structure, all at the nanometer scale, 100 nanometer kind of scale. And here we're looking at reflectivity curves for all of them. The one that extends the longest range from 10 to 80 is the offline system, and there's the online system static and the online system moving, and you can see we get good agreement for all of the samples. So the system works as predicted in terms of speed. Right now, what we're planning to do, the first version of this, we're going to scan the whole thing across the web, so we can measure one line on the web and we move it around. What we're aiming to do in the future is go to essentially multiple beam spots to do this, so that we don't have to move this. We actually have the whole web. We have a number of points along the web, and we only have to move it if we want to move it over the distance between points instead of the whole web. So the current status is we demonstrated single point high-speed measurements. To cross the web, we have to move the whole apparatus over the web, which is our plan for the first demonstration. But we're working on this multi-point system, which will eliminate that cross-web motion. We have 2 patent actions, one application and one provisional that we're now in the process of converting into a full application. And we are going to be participating in the New Mexico Rainforest Innovations I-Corps program that Lisa told you about earlier. This fall, we have applied for the national program. So far, the feedback has been very positive, but we don't know anything for sure yet. And the next step we're looking for is an NSF Partnership Innovation Program. And we need an industry partner for that. So if there are any interested people listening to this, please contact me. Okay, that's where I'd be. So are there any questions?
Yep, well, thank you for your presentation. So we have one question. What is the effect of temperature variation in measurement accuracy?
Well, that depends on what materials you're looking at and how sensitive they are to temperature. But the temperature in these processes is pretty well controlled, so I don't think there's any issue there.
Okay, and then one more question we have is, do you require periodic or real-time calibration for a temperature or heat effect?
You require periodicity, and obviously if the material if the period changes, that's going to change the reflectivity. So yes, you would have to monitor that in some way, but that's pretty easy to monitor. I mean, it's easy enough to measure a diffracted signal and figure out what your period is.
Okay, great. And we don't have any more questions, so thank you for presenting.